My name is Theodore. I'm the director of IDEA StatiCa UK, and I would like to welcome you once more to our Connection Wednesday. So if this is the first time that you're following one of our webinars, Connection Wednesday is our regular online meeting that we do every 2 weeks. And the scope is to provide as much information as possible about this new technology, this exciting new technology about structural design and check of all steel connections. All of our previous webinars have been already uploaded on YouTube, so if you want to follow, if you want to watch any of the previous ones, you can find them on our website. So before I introduce our presenter for today, I just wanted to mention a couple of things about GoToWebinar. This is the software tool that we're using for the broadcast. If you haven't used it before in the past, it's pretty simple. So on the right side of the screen, you can see a control panel, and this is where you can enter any question that you have during the webinar, because by default, all the participants are muted. So if you have anything that you wish to ask, just write it down and we will answer it as we go along. So our presenter is today is Kostis. Kostis is our support manager at IDEA StatiCa UK, and he's going to show you the two examples that we have prepared for today. So before we start, let's just make a small overview of what we're going to show you today. So in the first part, we have a customer example, and today this customer is Mott MacDonald. Mott MacDonald is a company that I don't think that we need to, it doesn't need a lot of introductions. It's one of the biggest consulting firms globally. And the example that we're going to show, multi-planar hollow section joint that you can see on the slide, which is part of a very interesting project in Jakarta, which I will talk a little bit more right after that. So the next part, the second part is, as always, the HelpDesk customer case. So we choose one question, one request that we had from one of our clients, and we chose this example today because it simply highlights one of the powerful features that IDEA StatiCa has, and this is the general anchoring. So let's begin with the first part. So as I mentioned earlier, Mott MacDonald doesn't really need a lot of introduction. It's a global engineering, management, and development consultancy firm. It is active in 150 countries around the globe, and it was ranked in the 13th place in the top 225 international design firms globally for 2017. And usually every year it is among the 10, 15 bigger companies, let's say, in that list. It is active in practically every aspect of the AEC industry, as you can see on the right. So buildings, infrastructure, highways, oil and gas, power, tunnels. So everything, every different, let's say, aspect of the construction sector, Mott MacDonald is active there. And it has been our client since the beginning of 2017, of course, one of the biggest customers that we have in the UK at the moment. So today we're going to present one of Mott MacDonald's projects. Actually, we're really happy to present this example today, which is the Jakarta International Velodrome. This is a sporting venue that is being constructed at the moment for the 18th Asian Games in August 2018. And we're actually happy for two reasons. One is the fact that we can show that IDEA StatiCa is used by global leading engineering firms who trust it to deliver these challenging projects. And the second is that we can actually show one of these projects, and a recognizable one, which is, in this case, this velodrome, and how it has actually helped Mott MacDonald to deliver this. This velodrome has been a very challenging project, mainly for two reasons: because of a limited budget and the time frame that it had, but also because it facilitated the reuse of two temporary venues from the London 2012 Olympics in order to form this venue, which will be a permanent structure. So reuse of materials in the steel industry has become a major topic lately, and this project is a very good example of this trend. So two venues: one was the water polo venue for the Olympics, and the other one was the shooting venue. They were used, parts of these two projects were actually used for this velodrome in Jakarta. This project was taken on by contractor ES Global. ES Global is actually a global leader in temporary venue construction, and together with Cox Architects and Mott MacDonald, of course, they who provided the necessary design expertise. The connections of this steel structure were designed with IDEA StatiCa, and they were actually took advantage of the beam interoperability that we have, not only we, but mainly all the software, between digital design models. In this case, it was Autodesk products that they were used, like Autodesk Revit and robot structural analysis, for example. And as you can see in this slide, these are the design workflows that have been followed. So we had a central building information model, and this model was used to exchange information between the different disciplines. As you can see on the right, on the top right, IDEA StatiCa was part of this workflow, and it was used for the connection design. More specifically, the connection nodes were imported from Autodesk Robot. That was used for the general, for the global model, for the analysis of the global model. And then the geometry of the nodes with the cross sections, the orientation of the cross sections of the members, and the loading were imported into IDEA StatiCa, where Mott MacDonald did the design, and then these details were used in Autodesk in AutoCAD in order to produce the final model, which helped for the installation of the structure. So in this example that we're going to show today, we're talking about this connection between the main column and the main beam. It's a multi-planar hollow section joint that is consisted of 8 CHS members, which are all welded together. So without any further delay, I will switch over to Kostis, who is going to show this example, how we can model this from scratch and design it according to the Eurocode. So I'm going to give you, Kostis, the screen.
Okay, hello everyone. Theodore, can you confirm that you can see my screen?
Yes, perfect.
Okay. So I think that Theodore already mentioned that this is a multiplanar hollow section connection. As we know, for this type of connections, it is almost impossible to be solved with the analytical models that are offered in the codes. So we need to find another solution, like IDEA StatiCa, for example. And for modeling this connection, we will start by following the original BIM workflow that was used by Mott MacDonald. And we will model the joint from the Autodesk robot BIM link output, which you can see here. The BIM link approach has two advantages. First is that I can have the correct orientation of the members easily, which is essential for this type of connection and saves us a lot of laborious work. As you can see here, for example, the member angles have been inputted from the software with a precision of up to 5 digits, which would be too much work. And second is that we have automatically inputted the loads on each member for 8 load cases that come straight from Autodesk robot. Since the results of this case come straight from a global analysis model, they respect equilibrium and make sure that the exact stress calculated at our global analysis is correctly replicated in IDEA StatiCa. One more thing to notice about this joint is that it was built, initially it was used in the UK, where we have the European steel grades, and then it was moved at Jakarta, where it was designed using the American codes, which you can see if we go at the project items. And for this, we are currently using the American codes with metric units. And of course, we have a needed of the A36 steel grade, the American steel grade, which actually is the S355, as you can see here. So let's go back at the design and start modeling our connection. I will switch my view to transparent. And first, I will connect the head vertical at the column. For this, I will use a meter cut. A meter cut is a newly introduced feature in IDEA 8.2 release. And it let us essentially connect to members by welding them. I will also rename my manufacturing operation. And then, after I have welded these two elements, I will weld the arch bottom cord. Again, I will use a cut. I will rename this to arch to a mate. Okay, so that I can connect this horizontal member here. Again, I will use the arch bottom cord and the M8 member and use a meter cut. Then I will connect the horizontal M8 and arch bottom cord members at the head vertical and the column. Again, I will use a cut. I will name it to arch to head. I will cut member arch by head. And for this, I will use the surface cutting method. And you can see how this is shaping up. I will replicate this, and I will use it to connect my arch to the column. And for this, I have to switch the head vertical at the column. And you can see the change of shape. Well, I forgot to switch my weld type to butt weld at both of these operations. I will do it right now. And then I will proceed with member M8, and I will connect it by replicating this operation. I will rename it M8 head, and I will just change the arch bottom member to M8. I can verify by the shape of my connection that this is what I wanted to do. Again, I will copy the other part, M8 to column, and I will change the arch bottom member to M8. Now that I have connected my almost horizontal members at the vertical ones, what I have to do is connect these two splits here. These splits are connected at member M8. Again, I will use a cut operation. I will rename it to split 1 to M8. And again, I will use the surface cutting method. Okay, I can see the shape, and I will switch to the solids view in order to verify the position of my weld. Okay, for this I will use a fillet weld. As I told you before, we're working in the American code, so I'm defining a leg size for the weld, which is 9.9. And again, I want to replicate the connection of split 1 at member split 2. I'm copying the operation, renaming, and changing the member to split 2. Okay, you can see the weld and its leg size. And last, I have to connect my head braces. Again, I will use a cut for head 1, head brace 1, and head brace 2. I will use a meter cut so that they're connected together here. And I will start with head brace 1. Okay, and I will weld head brace 1 at member M8. I will define the members using the surface cutting method. I see that my welds are where I want them, and I will define leg size here. I also want my head 1 member to be connected at the head vertical, so I'm replicating this operation. And I'm changing the cut by to vertical. Again, I will copy the last two operations for member head 2. I will rename the last operation. And then I'm changing the head brace to head brace 2. And here it is. The connection is ready to be solved. In order to solve the connection, I will go at the check tree item, and I will press the calculate button. I will skip the solution because of the time limitation we have, and I have already opened the already calculated file. If I go with the check and I activate the overall check, we have the picture that the software shows us after the solution is over. This is the so-called traffic light check, where we have 4 colors. The gray color is for low stressed members, meaning that their utilization is less than 60%, like the head vertical. We have green for average stress level, meaning more than 60%, but less than 95%, where you can see the arch, member M8, and the splits. And last, we have the orange for stress close to the limit, but still passing the checks, meaning that the utilization here is over 95%, but still less than 100. Fortunately, we don't have red parts, which means that they're failing. We also have an overview of fault checks. In this summary table here, you can see that the analysis has a value of 100%, meaning that the solution has converged. All plates are below the 5% plastic strain limit, with the highest being 3.3%. And all welds have a utilization lower than 100%, with the highest being 78.4%. We can go deeper at the relevant tabs. For example, I can go here at the plate. Let's switch the view transparent, and if I select a row here, a member is selected, and on the top 2D view window, I can see the unfolded plates of the selected member. I have selected head brace 1 here. In the table, we can see the thickness of the head brace, the critical load case. We can see the equivalent stress, the maximum equivalent stress of the head brace, and the maximum plastic strain. If I activate the equivalent stress button, I can see the exact equivalent strain distribution all over the member for its critical load case. And of course, for this critical load case, I can see the distribution of equivalent stress all over the 3D structure here. If I change this to, let's say, split 1, both the 2D view and the 3D view change to match the other critical load case for split 1. The same is valid for plastic strains, which, as you can see, are quite low in this case. Now, what's interesting is this plastic strain check, which shows plastic strains with the traffic light check. Now, let's select something interesting here, like the head brace, where we can see the utilizations here. And after that, I can activate my deformed button and the mesh. And I can see the deformed shape of the structure for the critical load case of the selected item. Last, we have the welds. The weld results are shown in a table for each weld and the structure. But what's interesting for the American code is that we can unfold, let's say, a table row, and we can see the formula calculations. These formulas can also be printed in our report. And with this, I conclude this part of the presentation. and I will return the presenter to Theodore.
All right, thank you, Kostis. So, good. So yeah, before we proceed with the next topic, I would just like to say many thanks to Matthew Pierce, the principal structural engineer at Mott MacDonald, who provided us with all this material, the project, and all the information about this project in Jakarta. So thanks a lot, Matthew. And let's move on to the second part, which is the HelpDesk highlight. So today's example is the joint that you can see in this slide. This example was sent to us by one of our clients. So as you can see, although it seems like an easy, let's say, not a really complex connection, it's quite tricky because it's not the standard base plate with a column, but it has a beam, an horizontal beam, which is bolted on a base plate on top of a concrete column. So seems quite easy, but it's quite complex at the same time. We chose this example because it highlights one of the powerful features of IDEA StatiCa, which is the general anchoring that was added in the latest release, which allows us to model and design any kind of anchoring. As you can see in this example, this has also it is a standoff beam, so it means that the beam is not directly welded to the base plate, but it's rather it has a distance, it has an offset from the base plate. So this is also a feature that we can model in IDEA StatiCa. So let's switch back to Kostis, who is going to show you exactly how we can model this type of connection.
Okay, thank you, Theodore. Please verify that you can see my screen again.
Yes.
Okay. Now I have opened the original file that the client have sent to the help desk. He was trying to calculate this connection. And this is a connection that was impossible to be correctly modeled before our recent 8.2 release, which includes our general anchoring solution, among other things, which I will demonstrate right after discussing this connection as modeled by our client. So here you can see the initial efforts of our client. And if I go to the design tree item, you can see here that he used almost 30 operations to model this. Nevertheless, this approach does not provide an adequate representation of the structure stress, because first, this is loaded like a column and not like a beam. And the loading is a little bit awkward because the loads flow through the web of this beam and then are distributed at the plates, which are welded after to shape the I section. And because this is not a standard I section, he had to create all these operations just for the stiffeners. So one last thing is that if I view from the Y direction, this is slightly inclined, okay, which is important for the modeling. Now let's go to the project items, and I will create a new connection where a new project item where I will try to replicate this. First, I will add a beam. I will change the name to beam, and I will use a built-up cross-section for this. Sorry, a built-up cross-section with a height of 380 millimeters, a thickness of 20, a width of 210, and again a thickness of 20. My beam is set here. I will set it to continuous and its overall length to 880 millimeters like in the original file. I will then set its direction to 90 degrees and I will rotate it by 15 degrees just to have the same orientation with the original file. Now let's go at the design tree item where I will create the anchors. I will use a bold grid operation, which I will rename to anchors. I will change the fastener type at anchors, and the item count will be 1. It will be a plate on member beam, and it will be the bottom flange. I will change the view to transparent. And now I have to define a foundation block. This new foundation block will be related to my member beam. It will be positioned at its bottom flange. And I will use different offsets for the longitudinal direction and the lateral one, just to match the original connection. Its depth will be 200 millimeters. But most important here, I can define a gap of 30 millimeter thickness, which was a requirement. Then let's define my anchors to 1600 millimeter like in the original file. The anchor type will be a washer with a rectangular plate. I will position the rows like in the original file. Let's set the other positions too. And here it is. Next, I will add some stiffeners. The stiffeners will be on my beam. They will have a thickness of 20 millimeters and a double fillet weld of 5 millimeters. I will start positioning them from minus 210 millimeters, and I will repeat it 3 times with a distance of 140 millimeters. I will create a new stiffener for the last one because it does not have the same positioning distance. And after I have positioned them, I can always go at the bill of material and have a view of my anchoring solution here to see if it's the same as the required one from the client. Let's go back to the design. Now that our connection is over, we can load and solve. For this, I will go to the load effects. And now the first thing I will do is I will activate the check equilibrium button. Since this is a base plate connection, let's say, we have one support at the farm, which is our foundation block. So when I add the load case and also have the check equilibrium activated, I can load my beam at both ends. And now let's add some random loadings here. Let's minus 50 in the other end and 50. So let's go with the check and calculate this one. Again, we can see our traffic light check. I will not repeat this, but now something interesting is here at the concrete block. You can see the utilization of the concrete block is 0. And the reason is that we have a distance from our anchors, from the foundation block. And if I go again at the anchors tab, here I have two tables. The top table shows the anchors in tension, and the bottom table shows the anchor in compression. And I can also see this if I make sure that the strain check is activated and also the both forces. And here you can see the forces at our anchors, which are both compressive and tensile. So with this, I conclude also this part of my presentation, and I will give the presenter back to Theodore for our Q&A session.
Thank you, Kostis. Good. So let's see if we have any questions. I see that Adam has already answered all of them. So for any of you that haven't actually used the software until now, we strongly, let's say, encourage you to download our free trial, and so that you are able to see for yourself all this potential that this software has and the new possibilities that it offers when it comes to steel connection design. So you can just go on our website, ideastatica.com/free trial, and apply for a trial. It's a full featured version. That means that you have all the features that are available in IDEA StatiCa, and the only limitation is the time. So you have 2 weeks to test it out. At this point, we're coming to the end of the webinar. So from all of us in IDEA StatiCa, I would like to thank you again. We appreciate a lot the time that you took to attend our webinar, and we certainly hope that it was interesting. So if you want to join us next time, the webinar will be on December 13th. So in 2 weeks from now, you can register for this webinar as well. We are going to show different examples as always. And of course, if you are already using the software and you have a project that you would like us to present in one of the next webinars, we would be more than happy to do it. So please send it to helpdesk@ideastatica.com, and we will make sure that it will be presented in one of the next Connection Wednesdays. So again, thank you very much for joining, and we hope to see you again soon. Bye-bye.
Bye-bye.